That is a very typical single degree of freedom vibration system. And however, in this example, if you look at my drawing here, and we want to consider the influence of the mass from the spring. So before, we always assume the spring has no mass. And simply spring contribute is spring constant, that's it. But for this case, we do want to consider the spring has the mass. So here we consider the whole spring has the mass ms. And the mass block is m. So here we have two mass blocks. This one still belonging to the single degree of freedom, because here we define our degree of freedom is x, representing the x here. So let me enlarge the drawing. So here let me put the mass, the spring. Let me put the free body diagram. Of spring. Okay, so the spring is kind of here. So this end attached to the mass here. So that is this point here. Okay. So right now in our definitions, we say we define the degree of freedoms x as the end of the spring. So at the end of the spring, that has that much of the, say, the degree of freedom x of t, right? And the spring, we're assuming that is a uniformly distributed mass system. So on the top here, basically the mass point of the spring doesn't move. Okay, so now let me say to draw. Basically, from here, you can imagine once the spring is stretched, then the mass point on the spring basically evenly redistributed according to how big we given the degree of freedom. So let me do this one here. At this point, assuming, let me convert the information. At this point, the displacement is xt. Okay. And at any point, let me pick up a small element and say the distance we measure from the top is y. And let me say this small element of the spring is called dy. Okay, so for this small element, we should be able to know its displacement basically is in the similar triangles. Okay, so for example, the whole length of the spring equal to how much and equal to L. Okay, so that means we'll compare to this little triangle with the bigger triangle. From here you can see y over L simply is equal to x, let me say the distance here is what I want to obtain. Let me say question mark and respect to x, right? Okay? So in this way, this question mark is how much this one will be equal to y over L times x. Okay? Okay. So right now we have that one, then we can begin to add it on, because that is a small mass. I almost say small mass. It's a small mass of the spring, and then that going to vibrate. It's going to have a kinetic energy. That little amount of kinetic energy must be added up to whatever the whole mass there. So we, in this way, our energy from here we have is this. Again, in these questions, we're going to still using the equation is the T max equal to the U max. Let me pick up, because in this way we only want to find the natural frequencies. It doesn't ask for the equation motion, so only for natural frequencies. Let me pick up this one. So where we formulate the kinetic energy. Kinetic energy, the first one is from the movement of the mass, and that is mx dot square. Okay? And the second portion is from the integration of the mass of the small element. So from here, we focus on this small element here. For that small element, and we know that for the whole spring, the total spring, the length of the mass, the length of is proportional to the whole mass, right? So that means for this little mass is how much? Simply is dy, right? Good. So that means this little mass basically is dy, the portion of the dy over L multiplied with ms, right? So here, in this way, I kind of calculated is what is this little mass here. You good? Okay, so it's 1/2 of the mass, and that is the dy over L times ms. That is the mass, and 1/2 times mass times corresponding velocity square. Sorry, and the corresponding displacement is such big, so its velocity simply is take a derivative. So that is derivative y over L times x dot and square. Right? And then we integrate, that means that is small amount, we simply integrate. And integration is from y from 0 to L. Basically, the second term is will give us the total kinetic energy contributed by the mass, by the spring. Okay? Any questions? Good. So in this way, we do these things, and you do the integral. Right now, your integral has a dy, so we can integrate. And L and ms is a constant, so only have y is changing, x dot we can turn out. So basically, this one will be equal to 1/2 plus okay. So that is the kinetic energy, and the total energy of the spring is simply here is simply take the kx dot square. Okay. And you might ask me, why not we take the differential consideration for the spring, for the strain energy? Yes, we can do it. But here, let me skip the complicated process. We just assume we can take this bulky term, okay, just for demonstrations. So with those things, and then we can pretty much there. So right now, again, we let the xt. Again, we know that this is a harmonic motion, so we have the xt will be equal to x times cosine omega nt minus v. So therefore, x dot will be equal to omega n x and sine omega nt minus v. So therefore, with this assumed forms of the systems, then we know the Tmax will be equal to simply is we plug in 1/2 m plus ms over 3 times the maximum velocity simply equal to omega n times capital X squared. So right now I have introduced is the maximum value of these terms by this. Good. The maximum velocity x maximum dot equal to omega n times x. Okay. And then the potential energy maximum is 1/2. Okay. The maximum value equal to x squared. So again, from here I introduce the maximum value of this field here because from this case, the maximum of this one is capital X. Okay, so I think it would be better for me to distinguish this as capital X. Okay. So therefore, you compare this one, then by T max equal to the U max, then you can see the omega n will be equal to K m plus m s over 3. That is this number here. Okay, so that is for this kind of interesting questions, and our textbook provides very detailed, kind of spend a couple pages of the explanations, but that pretty much is covered here.